Hello viewers, welcome to another edition of Pause and Ponder. If you remember, last time we had asked you a question about the cola and soda water bottles. When salt is added to them, there is an evolution of carbon dioxide. We asked you to answer this question. The explanation is very simple. When you add salt, it is more soluble in water, so it displaces some of the dissolved carbon dioxide, and that is the reason why carbon dioxide is evolved. This is called salting out. A similar experiment is made use of in salting out of soap. Soap is soluble in water, but if you want it in a solid form, you add salt, and so the soap separates out. This process is known as salting out. In today's Pause and Ponder, we are going to talk about polymers and network formation. This is one of my favorite topics. In the early days, they used to say the country is most civilized which uses the most amount of sulfuric acid. Nowadays, we say that country is most civilized which produces and uses the most amount of polypropylene. We have come a far way, no doubt, but all this started in 1846 with a very fortunate accident. Christian Schonbein, a chemistry teacher, was working in his kitchen when nitric acid was spilled onto the floor. Not finding a mop, he made use of his wife's cotton apron to mop up the mess, and after washing it, hung it close to a fire to dry. To his amazement and surprise, the apron vanished, and that was the beginning of the inquiry into the field of polymers. The first use of this material, which was nitrated cellulose, was in smokeless gunpowder. In 1889, Count Hilaire de Chardonnay produced fibers from this cellulose nitrate or nitrated cellulose, which is the common name, and they were exhibited in the Great Paris Exhibition. However, these fibers caught fire very easily and were also labeled mother-in-law silk. The first synthetic material to be produced, totally synthetic material, was in 1909 by Leo Henrik Baekeland, who produced Bakelite, a reaction product between phenol and formaldehyde. What we are going to do today is to explain network formation with the help of three simple experiments. I will make use of two of these copper discs to stick them together like this instantaneously. I'll make use of polyester resin, which is unsaturated polyester resin, and normal polyvinyl alcohol, which is used as a stationary adhesive, and we will see how each one of this produces a sort of a material or a substance which in one case will be hard, in one case it will be soft, and the discs just cannot be separated. All this is possible because chemists have found out a way of tailor-making the polymers to give certain properties. These two copper discs which I have in my hand, what I will now do is place a drop of a super adhesive in between the two, bring them together like this, and within a matter of a second or two, I will not be able to separate this out, and neither will you, simply because it would need at least 1 ton per square centimeter force to separate the two. Now, what is the explanation? The adhesive that I am using is chemically called alkyl 2-cyanoacrylate. When alkyl 2-cyanoacrylate is put onto this, and when I close the two discs together like this, it polymerizes to form long chains and develop strength. That is the simple explanation. What we'll do is place a drop of cyanoacrylate adhesive onto that copper disc, pick up the other copper discs, And that's the end of our experiment. Now let's lift this and try to pull it apart. Let's see what happens. In our next experiment, I'll be making use of this liquid, which is a viscous liquid and is called unsaturated polyester resin. It is a polymer which has been dissolved in a reactive solvent. Now we will make use of this liquid and two other chemicals. This is called the promoter. It's a purple colored liquid, and this is called the catalyst or the hardener. Just now I am not going to mention the chemical names simply because this is a general program and not a polymer chemistry program. So when I add these two liquids into the polyester resin, mix it up, you will see that the entire mass will turn into a hard plastic material in a matter of minutes. Now what we'll do is, we'll transfer this polyester resin in a reactive solvent into this beaker. This beaker appears cloudy because I have coated it with wax to help me demold the product afterwards. You can see this whole mass has turned into a solid. I am trying to take it out, but it is not coming out easily. So I'll invert the entire thing, and what do we find? We find that no liquid comes out, it is turned into a solid, and the solid looks like this. Cross-linking or network formation. Network formation is a process in which the chains of the polymers interact with reactive sites on other chains, forming a tightly bound three-dimensional network. This network has the characteristics of very high melting point, good mechanical strength and chemical resistance. Our last experiment is with stationary adhesive, which is easily available in the market, and we need another chemical which is called sodium tetraborate, ordinarily known as borax. What you do is you take a beaker or container or any suitable container, take this adhesive, pour it into the beaker or container, now all we need to do is add a saturated solution of borax, sodium tetraborate. This is borax, this is water. We have added water and shaken it for a long time. Whatever borax has dissolved has given us a saturated solution. And now I'll add it and stir it. So here goes. And what do you see? Immediately, the whole mass has turned into a gel. Let me add a little bit more. And there you are. The best description I can give you is that it looks like halwa. Here you are. This is another explanation, another experiment for network formation. But the difference between this network formation and the earlier one is that this is soft, whereas the other one was hard. A clear example of structure-property relationship. Let us summarize the entire presentation. In the first experiment, a drop of the adhesive bonded the two copper discs together and we were not able to pull out. We said that this was on formation of long polymeric chain. Then we made use of polyester resin, unsaturated polyester resin, and it turned into a hard solid. When we inverted the beaker, nothing fell out, and therefore we've got a hard solid which we call network formation or cross-linked polyester. And finally, the last experiment was with polyvinyl alcohol and borax, and we got a soft network. Why are there so many different forms of networks? This is simply because of what we call structure-property relationship. Different structures of chemicals used produce different properties in the chemicals produced. Simply, the chemist is able to confer properties at will on polymeric material. The next time when you switch off your light, you are touching urea formaldehyde network polymers. When you hold a pressure cooker handle, you are holding phenol formaldehyde network polymers. When you touch your air cooler body, it is unsaturated polyester network formation material. Next time, pause and ponder as to how important these polymers are in your life. Write to us at Pause and Ponder, care of Audio Visual Research Center, Usmania University, Hyderabad 500007.